Okay, let's understand about the projections. Now, I would like to ask you that what is the basic goal of CG? The basic goal of CG is to provide realism. Okay, and now what is projection? Projection is nothing but resolving n dimensions to n minus 1 dimensions. So there can be n dimensions. We have usually we have this thought of being uh, usually we have this thought of working with one dimensional, two dimensional, three dimensional and four dimensional, but there can be n dimensions. And projection is nothing but converting a four dimensional into three dimensional, or a three dimensional into two dimensional. Now regarding the three dimensional, we have three things, that is the x, y and z. A three dimensional can be explained by a space, whereas the four dimensional include one more factor, that is time. So let us take an example about a 2D basic structure. That is, we have an x-axis, we have an y-axis, and this is the origin. So I'd like to take an extra point, that is A, and we are going from 0 to A, that is origin to A, and we are marking this distance as r. So we have a y, that we can mark this point as 0 comma y, and we can mark this point as x comma 0. So in this diagram, according to this diagram, y can be understood as a perpendicular, whereas x can be understood as a base, and r is an height. That is a hypotenuse. This is actually wrong. We could consider as hypotenuse. And now the basic structure is like perpendicular, then base, then perpendicular, and down we have hypotenuse, and base. So we have a basic structure of sine theta, cos theta and tan theta, and according to this formula, the perpendicular upon hypotenuse, what is the perpendicular here? The perpendicular here is y, whereas the hypotenuse is r, so we could write this as y upon r. Similarly, base upon hypotenuse, what is the base? Base is x, and hypotenuse is r, so we could write this as x upon r. So this changes into a formula which is called as y is equal to r sine theta, and this changes into a formula called as x is equal to r cos theta. Now we know what is the value of y and x. We know value of y is 0 comma y, and the value of x for this particular diagram is x comma 0. So we get an equation as y is equal to r sine 0 r sine theta comma 0, and r cos x as r cos theta comma 0. So what have we done? We have basically converted this 2D into a 1D. So this is what projections deal about. We usually convert this n dimensions into n minus 1. We have converted here a 2D into 1D. Another thing is that while converting a projection into from 3D to 2D, converting in a 3D form into 2D, here's an example where I have taken a sphere and I have converted into 2D. And while talking about 3D things, we have three factors, that is the x, y and z. And while converting it into 2D, I have some loss of information. So in 2D I have lost this z. You can see this sphere has converted into a ball, and this loss of information is nothing but rendering. While working with projections, when we convert 3D into 2D or a 4D into 3D, we have some loss of information, and this loss of information due to projection is called as rendering. So we have till now understood that projection is basically converting a 3D into 2D or a 2D into 1D. While converting this 3D into 2D, this loss of information should be compensated with some things, and in order to compensate these things, we include factors such as the shading effect. For example, we could consider our eyes. Our eyes also work in a 3D. See, the world around us is 3D, while the retina frame is 2D. So in order to compensate with this projection, to give a realism effect, the eyes consider factors of colors and depth, etc. Here are some components required to have an projection. So basically we have a viewport. This frame is called as viewport, where the projection will be carried out. We have a center of projection. This can be a eye, a viewing thing, eye or something, and this can be a object. Here I have taken a 3D sphere which I have which I have taken as an object, a 3D sphere, and there will be some rays coming out from the projection center of projector to the sphere. So these rays are nothing but called as the projectors. These rays are called as projectors, and the point where the projectors meet intersect the viewport from the object is called as the point of intersection. This here in this example I am converting a 3D object into a 2D. And for example, you could take a pinhole camera, the example of a pinhole camera. This can be a working of pinhole camera. Now usually while drawing a line from point P to Q, we need to mark down all the points that come between P and Q, and this can be done by using the formula y is equal to mx plus c. But while working with projections, we need some different formula, that is a parametric equation. What is the parametric equation? The parametric equation for this regarding this projection is P plus T bracket Q minus P. So here the T is a parameter which keeps on changing. T is a parameter which keeps on changing. See, you can see that if I put the value of T as 0, I could easily find P. If I put the value of T as 0, I could easily find point P. Similarly, if I put value of T as 1, I could easily find point Q. You can see how am I finding point P? That is, I'm just replacing this T by 0, and I'm easily finding the P as P and P gets cancelled. And similarly here, while putting the value of T as 1, I am easily able to find the value of Q. And this is how we are able to find all the point of intersections working from Q to P. Now another topic included in this is, till now we have seen an angular projection. There's an angle created between this, and thus it is called as angular projection. And all the angular projections are nothing but perspective projections. Understood? All the angular projections are nothing but perspective projections. Now when we move this object far from the center of projection, the object becomes smaller and smaller, and there comes a point where at infinity the object is very much parallel. These rays of light, that is the projectors, become slowly parallel, and at a point of infinity they becomes invisible, almost invisible. So we could consider that when an object is at infinity, the projectors become parallel, and this is termed as parallel projection. So while representing a parallel projection, we need another equation, that is E plus TD, where D is a direction vector, that is the direction vector of the object or the viewpoint, the direction vector of the object or a viewer. So basically we have seen the classification of projection. We understood what is perspective projection and parallel projection. Perspective projection includes all the angular projection, and when the object moves at infinity, it becomes parallel projection as the projectors become parallel to each other. Okay, now in parallel projection we have another two types, that is the oblique and the orthographic projection. In oblique projection, the projectors are parallel to each other, but they are not perpendicular to the view plane. This is the view plane. They are not perpendicular to view plane. They are projectors are parallel to each other, but they are not perpendicular to view plane. And in orthographic projection, the projectors are parallel to each other as well as they are perpendicular to the view plane. So this is basically the main difference between oblique projection and orthographic projections. Now under orthographic projections, we have another types, that are axonometric projections, isometric projections, diametric projections, and trimetric projections. Now under axonometric projections, what are axonometric projections? Or axonometric projections are all three faces of an object are visible at an instance. Like you could see all the three faces, that is the x, y and z of an object in a single instance, or you could see all the three faces, that is the x, y and z of an object in a single instance. That is axonometric projections. And while talking about isometric, diametric and trimetric, we need to first understand what is the foreshortening factor. What is foreshortening factor? See, there is a formula that height of an image or the size of an image upon size of an object. Now for example, we could consider the mapping the satellite mapping, wherein they need to scale some things like the distance between two cities, that is 100 kilometers, could be represented in 1 centimeter. So this is basically scaling, the scaling in isometric projections. The x, y and z all are same. While scaling, x, y, z are all are same. In diametric projections, any two of them are same. In any condition, any two, either it is x and y, either it is x and z, either it is y and z, any conditions, any two of them are same in diametric. And similarly, as the name suggests us, in trimetric all the three are different. In trimetric projections all the three are different. Thank you. So guys, I am Dharmik Konar, and if you really like the video, you could tap the like button.